is web assign 8C, number 7, and it read, a 0.29 kilogram block resting on a frictionless horizontal surface is attached to a spring whose force constant is 83.8 Newton meters, as in the figure below. A horizontal force F causes the spring to stretch a distance of 4.52 centimeters from its equilibrium position. And part A reads, find the magnitude of F. So, to do this, we are going to, so since it's a spring, Hooke's law says that the force is equal to the spring constant times the displacement of X. So, you can say it gives the spring constant 83.8 Newton meters, and the displacement was 4.52 centimeters, and this is where you have to watch out because you have to convert. So make sure you convert, or else you'll get a different answer. Students always tend to forget conversions. And we get that the force is equal to 3.79 newtons. So for part B says, what is the total energy stored in the system when the spring is stretched? So when the spring is stretched, it has only the spring energy, so you can say that the total energy is equal to 1/2 k x squared. And so we get K gave us 83.8 Newton meters, and the displacement meters squared. So total energy came out to be 0.086 joules. Part C asks to find the magnitude of the acceleration of the block immediately after the applied force is removed. So the force stretches it out, and then it lets it go, and it starts to accelerate. So it's asking us to find that acceleration. So first, we can do this using work. So since it's moving, there's energy and it's work in the system, so it's doing work. So we can say 1/2 the force that's doing the work times d. So we need the force in order to find acceleration. So we can use F is equal to ma. So we'll solve for force here and then plug it into that equation. So we got that the work, this is also where some students get messed up, is that work is equal to the total energy here. So we just solve for the total energy, so we can put that in for work. 0.086 joules is equal to 1/2. We're solving for F. And then the distance, which we got earlier, 0.0452, meters. And after we solve that, we get 3.81 newtons for the force. And now we can just plug it into our equation over here. 3.81 newtons is equal to its mass, which is 0.29 kilograms, times A, and we're solving for A. And we get that A is equal to 13.13 meters per second squared for our acceleration. Part D asks to find the speed of the block when it first reaches the equilibrium position. So, as we know, when things oscillate, it's at its max speed when it reaches the equilibrium point, and max acceleration at the end at its max stretch. So we know that this will be its fastest. It will be at its fastest when it reaches the equilibrium position. So to find this, we can use energy. So can say that kinetic energy is equal to work. So, because when it's at the center, it's at equilibrium. When it's moving, it doesn't have that, the spring isn't stretched out, so it doesn't have that spring energy anymore. It's all kinetic energy. So we can say that 1/2 mv squared, the kinetic energy, is equal to work. And we solved for work earlier, we know the mass, so we can just solve for the velocity when it's at that point. So we can say 0.086 joules for work, and 1/2 0.29 kilograms times v squared. And we get that v is equal to 0.77 meters per second. And part E asks, if the surface is not frictionless, but the block still reaches equilibrium position, would your answer to part D be larger or smaller? So when you think about this, the answer is smaller. When you think about this, if a block is moving, if on a frictionless surface, it's moving and it gets there at that speed, and then friction slows things down. So if you add friction in there, it will reach, and it still reach at that position, it will reach at a slower time. Since friction opposes motion, it's slowing that block down. So the answer should be smaller. That was a hard question that some people get wrong. That they don't really know. They have to understand how friction works. And if I asked, what other information would you need to know to find the actual answer to part D in this case? You would have to know the coefficient of friction, since you want to see how much when friction is added, you need the coefficient of friction. And part G asks, what is the largest value of the coefficient of friction that would allow the block to reach the equilibrium position? So again, we can look at this with work and energy. We can say G work is equal to the static coefficient 0.29 for the mass kilograms, 9.8 for gravity. Oh, running out of room. 0.8 for gravity, and then x, because work is equal to force times displacement, right? So, and displacement we know was 0.0452 meters. So now multiplying that all out. Oh wait, and the work was, we got that the work was, we can use the same work from before, 0.086. 0.29 kilograms. And then we can just solve for our coefficient, which comes out to be 0.67. So there's a lot of energy in this problem, so you need to watch out for, I know energy can be tricky sometimes, so there's a lot of energy, work, and yeah, basically I learned, from this problem I learned that forces can be applied to help solve oscillation problems, and that when the thing that's oscillating is at its max stretch, it is at zero velocity, and then it's at its max velocity when it's at the equilibrium position, when it's passing through. And at the edges when it's max stretch, that means that the acceleration is at its lowest. It's like zero. Or no, sorry, scratch that. It's at its highest when it's outside. And then zero in the center for acceleration.